Hello, hello. There it. Hello, hello. Good after. Oh, she's got the double number one going on. We got the Vicky and the Joel and the Gabriel. Gabriel being I'm just
Good
saying.
morning,
Yeah, and the
Professor.
Lear. Good morning. Good morning. He's got the double with the video and the voice. We got the
Good
Vicky with the
morning.
double with good morning. Oh, Raina with the voice. Awesome. Good morning. Good morning. Gabriel with the not being late. Oh, did I? I didn't just say that. Okay. And Vicky with the video and the chat. And I'm gonna stop rhyming just like that. Wait, wait, people coming in, people coming in. And the Victoria with the avatar, and the Joel with the avatar, and the Sonam with the avatar, and the Aminata with the video. And that almost sounds like I'm kidding, yo. Um, but I'm not. And good
Good morning,
afternoon.
Professor.
Oh,
Well, good afternoon. Oh my gosh.
no, it's fine. And the Melanie with the voice and the metacognition. Yes. Good morning, Melanie. Awesome. And who else? And the good afternoon, Vicky in the chat, and the good afternoon, Gabriel in the double in the chat, and the good afternoon, Joel with the double in the chat. Good afternoon, Victoria with the double in the chat. By double, you know what I mean by double, yeah. Good afternoon, Raina with the double in the chat. Good afternoon, Caitlin with the chat. Good afternoon, Zoe. Good afternoon, Sonam with the double in the chat. Good afternoon, Aminata with the double in the chat. Good afternoon, David, and your iPhone. And good afternoon, Fabia. Good afternoon, Abid. And good afternoon, more people coming in. And I'm going to stop this madness in a second. No, I'm not. Wait, who else? Okay. Yes, good afternoon. And bear with me for a second. Good afternoon, Bridget. Thank you. Okay, we're going to start in a sec. Good afternoon, Lachman, with the all caps in the chat. Okay. Give me 1 second. Sorry. Well, we're gonna start. That will force me to start if I change the board. Yes. Okay, we're gonna start, but we're not because hold on 1 second. I'm sorry. There's a technological something. I know someone's in the waiting room. Sorry, 1 second coming. I promise, sort of, kind of. 1 second. Also, if you can't hear me right now, then that's a paradox. Hold on. Hold on. Coming, promise. Yes. Okay. Someone's in the waiting room. Okay. Okay. I want to move on to waves and all that stuff and staggered oscillators and what and lab three and all that, but I want to complete the package, the last sort of math tool that's really important in physics in general that we got to very quickly at the end of class yesterday, which is the cross product of two vectors. So I'm going to back up now. So I'm going to a little bit more slowly lay out some of the important implications of the cross product of two vectors. So let me warn you again. So this is me teaching now. Like this comes from the very last bit of homework too. Ideally, by the end of the class period, I'll like circle back and you know address some of those answers again, or the rest of the answers from homework two, but and you can remind me if you want to do that. Maybe you should remind me before time runs out for me to do that. But first, I just want to conceptually lecture about the cross product and something and some notation and vector things that I haven't said yet. Again, this is the last bit of sort of math. It's not the last bit of math, but the last bit of just isolated math that we just like need or love for physics. Okay, you don't have to like look for a connection to the physics material yet. Just try to appreciate it on its own mathematical level. Okay, so I'm going to do that. I'm going to, start talking about the cross product in a minute on the board. But also before I forget, I'm partly being able to do this because we could get back to waves and all of that tomorrow because we do have class. I just want to remind you, right, or confirm. My understanding is that we have class tomorrow at this time because tomorrow, and tell me in the chat if I'm wrong or there's something else I'm not, but I believe that tomorrow is Wednesday for all of us at John Jay. And to be super honest, like I find that like very difficult sometimes because many of us, including me, also live in other aspects of the world. And for example, me, like there's a hospital schedule and some medical, so it doesn't always work for me. But I believe it works for tomorrow. But I'm saying all that to say you should assume that we do have class tomorrow, but just keep your eye out. If something comes up with me medically or something, I will notify you. It might be in the middle of the night. If I can't do class tomorrow, I will notify you and like post videos and all of that. So, keep an eye out for that possibility, but don't get your hopes up or plan for it because I think we're on tomorrow. And if you don't hear from me, it means and it's a regular class, like where we're going to stay with the material, you get what I'm saying. So, yeah. Okay. So I'm looking at the chat. So, yep, yep, yep. Okay. So, yes, we do have class tomorrow unless otherwise noted. Okay, yes. So therefore, tomorrow we'll get back to waves, or we'll get back to staggered oscillations and try to start relating it to lab three. But right now, I want to finish this mathematical point about cross products. So, okay, thank you for your consideration in the chat. So notation. Okay, let's say we have so again, I'm talking about vectors here. Ultimately, what the ultimate point I'm going to try to make here is that when you're in a context of vectors, there's actually three different ways to do multiplication, three different ways to do multiplication when you're in a context of vectors. And each one of them is super important and different, but also in investigating three different ways to do multiplication in a vector context, when we're investigating the three different ways, uh, it becomes really useful for us to develop some further notation to help us describe vectors. And that notation then opens up understandings like in other areas, even when we don't think we're doing multiplication. Okay, so I am going to introduce some like symbols and things here. Oh, wait, so. Oh, yeah. And I'm sorry. Yeah. I totally see in the chat. It goes both ways. I don't mean to complain or be like weird. Like, yeah, we have class tomorrow. We're going to use it to continue with the material. But yes, what I'm also trying to say is I totally get it. If you guys also have other jobs or children or spouse, whatever, like seriously, like I get that your entire life is not John Jay. So if you have difficulties coming to class tomorrow or turning your video on or paying attention, no, I totally get that. That's really what I should be trying to say. I'm very sympathetic if it is difficult. And so don't worry about it, but just just watch the video, just stay with the material, like watch the video later. That's one of the advantages of all this. But for real, it's not personal. If you cannot make it tomorrow, I get it. Just please watch the video later and whatever. But yes, absolutely. That's in response to some direct chat stuff. Okay. So let's say we have two vectors, arbitrary vectors, A and B, and they differ, they're arbitrary, so they differ in size and they differ in direction by, let's say, an angle theta, right? So that's like the given, right? Well, first of all, I'm going to define right now. I think yeah, I guess I did this yesterday. Like, one thing is if you want to refer to just the raw, pure magnitude of vector A or vector B, then there's two ways of doing that. The fastest, simplest way is just to write the letter A without the vector symbol above it. Like when we do that in a vector context, that's not a typo, right? I mean, unless it is, but like when you're in a vector context and you write a letter without the vector symbol, you are explicitly referring to the magnitude by itself of the vector, like the length of the arrow, right? But the other way to do that is to put double absolute value symbols around the vector symbol. And often that's very useful, especially if, as you saw on the sheet yesterday, like if you're trying to refer to a whole combination of vectors or something like that. So either way, that means the raw magnitude without the direction, right? But now here's something that we may not have said before. And anything I say about vector A is also true of vector B. Okay, from now, I'm not going to do it every time, but right. But the other thing is, what if you want to refer to the raw direction of A without referring to the magnitude? Okay, this is a very important thing that some of you may have seen in another math class, but many of you have not. If you want to refer to the raw direction of a vector, you put a caret symbol over it, which we refer to as a hat, as silly as that is. That caret we call a hat in math and physics. So A with a caret over it is read out loud, A hat. And B with a caret would be called B hat. And what A hat is literally the vector A divided by its length. Okay? So A hat is a vector, but it is a vector necessarily like designed to be a vector with magnitude 1. In other words, and this is like this is a piece of notation, but it turns out to be a really important like idea, a useful way of thinking in math and physics that is very powerful. The idea is, say you have the vector, say vector A is 3 miles of distance pointing to the northeast, right? So the arrow is 3 miles to the northeast, and by like due northeast, like 45 degrees, whatever. So the unit vector for A would be 3 miles to the northeast divided by 3 miles, or divided by 3. So we would get a vector. So A hat would be a vector of 1 mile length pointing to the northeast, always on purpose. The unit vector for A would be a vector that necessarily points in the same direction as A, but only has a unit, a magnitude, a length of 1. So the idea of it is, so Okay, this sounds like I'm going in circles where it just like sounds like I'm not saying anything, but like I am. I'm saying from now on that if a hat is defined to be a vector divided by a, right? Like the whole arrow divided by the length of the arrow, then just multiply both sides by a, right? Then from now on, what that means is when you're thinking of the vector a, you can think of it as a monomial. You could think of it as a simple product of two values. You could think of vector A as A times A hat. And you're like, and if you're like me, you're like, great, thank you. Like, why do I want to do that? Like, okay, whatever. But what that means is, well, first of all, it means two things. It means, first of all, for all this time that we've ever been talking about vectors, like since last semester or whatever, we've always said in English, a vector is a quantity with magnitude and direction. And then like we keep talking about it in English, and then we do things with these vectors and we move them around and stuff. But like, first of all, for the first time now, I'm saying it's not just a rough English thing. It's not just like a vector is like sort of vaguely has a concept of direction and a concept of magnitude. We're saying from now on in, we can literally like capture that in a symbolic small, tight package where from now on a vector like A can literally be viewed as the multiplication of a raw magnitude A times a raw direction A hat. Like now it is a mathematical package that we can do stuff to. We can like add it to other packages. We can multiply it by other packages. Now we can symbolically capture both pieces of information of a vector in a mathematical, in a symbolically treatable form, right? So that's number one. Is that now I'm saying that from now on, a vector isn't just a magnitude and a direction. A vector is a magnitude times a direction, is what I'm saying. Okay. The other thing I'm saying, and I don't know how you maybe write that in your notes like somehow, but the other thing I'm saying more explicitly is this is a way to think about vectors now. It's like I'm saying now every vector that you ever imagine can be thought of as first a unit vector. Like if you're thinking of the concept of like walking 3 miles to the northeast, what we're saying is first think of a vector that has length one, like just think of a mile vector that just points to the northeast. And then imagine yourself scaling that vector up, stretching that arrow by a factor of 3. So you'll end up with an arrow of 3 miles pointing to the northeast. Like, in other words, from now on, we think of every vector as having been constructed from first a unit vector that pointed in a certain direction. Like we establish the direction first, and then we stretch or shrink, but we scale up or scale down that unit vector by a certain amount, and that gives us the final vector. And that's kind of why pure magnitudes are known as scalar quantities, because they are just the amount by which we scale up or scale down pre-existing vectors known as unit vectors. Okay, so this is a little bit abstract, I know, but excuse me. But I'm saying it helps. If you're going to go on in physics and math, it helps to start thinking of vectors as unit vectors that are scaled up or scaled down by a certain amount. So raw directions that are then increased or decreased in size. Okay, so I'll try to write that in. Right. So from now, I'm saying one more time, I'm going to move on. So from now on, the vector A can be thought of in our mind as the unit vector A scaled up or down by the amount A. Okay, that's the point. Now, also what that is, if you look at it, then this constitutes way number one of doing multiplication in a vector context. In other words, I'm saying, hence, Oh God, in a physics, it's all in physics. I'm sorry, in a vector context. Um, So I'm saying there's three ways to perform multiplication when you're dealing with vectors. And the first way is to multiply a vector by a scalar. It counts as a way of doing multiplication when you're in a vector context. And two things about it. One, when you multiply a vector by a scalar, you always get a vector. When you multiply a vector by a scalar, you always get a vector because all you're doing is taking an arrow and changing its size, and you end up with a new arrow. Okay. But furthermore, I'm saying if you're taking notes, please be taking notes. I'm not only saying that you like can do that and that you always will get a vector when you do that. I'm saying that in the first place, all vectors really are the result of doing that. And as long as you understand this idea of the unit vector. So the last thing I guess I'm saying is this new piece of notation, putting a hat over something, um, is a vector. A without any symbol over it is just a raw length. A with an arrow over it is the vector A. A with a caret over it is the unit vector A. It is a freaking vector. It has a direction and has a length. The length is one by definition. Okay, so that's way number one. Uh, Actually, oh wait. Okay, I'm looking at the chat. Okay, in fact, I'm going to say a little bit more now. Oh, and ways number 2 and 3 is what I have to go back to, but you know what they are. I mean, I'm going to write them down again, but way number 2 and 3, way number 2 is multiplying two vectors together to get a scalar. That's the dot product. And way number 3 is multiplying two vectors together to get a vector. That's the cross product. That's where I'm heading back to in a minute. But let me say one more thing about unit vectors, please. The one more thing to say about unit vectors is yeah, yeah, yeah. Okay. So I can say from now on, like the vector A is A hat. I could say the vector B is B hat. That like works and that's like tidy and it's like complete. But it doesn't really help me much relate A to B. Like if A is thought of as like some vector along the A axis that's scaled up, and then B is thought of as some vector like along the B axis and scaled up, like the A axis and the B axis don't necessarily have anything to do with each other. So it doesn't really give me a common coordinate system in which to relate A to B. So what we often do, especially in physics, is we first establish a coordinate system in which these vectors live, right? And the coordinate system, in three-dimensional space has three axes: x-axis, y-axis, z-axis, right? And they bear certain relations to each other. So I mean, you can rotate a coordinate system any way you want, but you can't like but you can't deform it. So So if you imagine from now on, like, for example, the x-axis, the positive x-axis coming out of the page at your eye, the y-axis going to the right, and the z-axis going up. Like, again, you could twist that or turn that, but it has to be self-consistent. If you imagine that coordinate system, then x hat would be a unit vector along the x-axis, right? And similarly, I'm sorry, yeah, well, yeah, and y hat would be a unit vector along the y-axis, and z. But they're so important. They come up so often, and x, y, and z already as like letters and symbols come up so overly frequently already in physics that in order to make it really clear what we're talking about when we talk about these unit vectors, we give them these new special names. I mean, so some people in the web, in some websites and in some textbooks, they will literally talk about x hat, y hat, and z hat. But more commonly in math and physics, we give these things a name and we call them I hat, j hat, and k hat. Okay, so this is a new piece of notation. Some of you have seen this, but many of you have not seen it. So let me be clear again. I'm not assuming you've seen this. I'm telling you like it wasn't in the homework or anything. I'm telling you it for the first time. But what I'm telling you is all triple equal signs. I'm literally just saying this is a new piece of notation that from now on, if you see I hat, it means X hat, which means a unit vector pointing along whatever we've declared to be the X axis. And similarly with J hat and K hat are the Y axis and the Z axis unit vectors respectively. Okay, so it's like a new piece. So that's a new piece of knowledge, but like now we have it. Or it's a new piece of construct, and now we have it. There's one other thing I was going to say about that. Is there one other thing? Oh, yeah. And like just to give you a quick taste of like what's the purpose of this, or like who cares or whatever. In this way, then from now on, if you have the vector A, you have the vector A pointing in some random direction, right? Like you remember from physics one doing like projectile problems or velocity problems or this or that. Frequently, it becomes really useful to divide A into two components, right? One that lies along an axis that you've already tacitly declared as the x-axis, and one component that lies along the y-axis. Now, again, if vector A was the only vector in a situation, there is no reason to make the x-axis anything other than an axis that points along A. Like, not to rabbit hole, but one of the huge principles of physics 1, of physics 203, is Galileo's principle of relativity. We get to choose our coordinate system, but we have to choose a coordinate system always in physics. We get to choose our perspective, and we want to choose a perspective that's the most convenient. But we do have to realize that no matter what we're doing, we're in some kind of coordinate system. So we have to be explicit about our choice and stick with our choice. So if you just had one vector sitting around, there's absolutely no reason not to align your coordinate. There's every reason to align your coordinate system and think of the A hat direction as like your axis, as your principal axis, as your x-axis, right? But once you have two vectors that you're trying to relate to each other, such as force and displacement being related to each other, right? You don't just automatically want to make the direction of the force be your x-axis. You want to relate the two vectors somehow. So you choose a coordinate system that has an x-axis, a y-axis, a z-axis, and you relate each vector to that, right? Like physics 1. So in physics 1, physics 203, you would say things like, oh, the velocity has an x component of v cosine theta and a y component of v sine theta, or whatever, right? But again, you would just like sort of say that in English and then do stuff. Now what I'm saying is we can be more explicit about that. We could say, when we take the vector A and it's at some angle, I'll just call I don't want to confuse you. No, sorry. I don't want to, sorry. If it's at some angle theta, might or might not be the same theta as on the other page, but whatever. If the vector A is at some angle theta, right? We used to say like that the x component of A was A cosine theta, and I'm still agreeing with that, but now I'm saying, well, let's be more specific. And similarly, like the y component was A sine theta. Let's be really clear what we meant by that then. What we're really saying is that vector A could be thought of as the sum of two tip to tail vector components, right? Vector A could be thought of as the sum of an AX vector with a plus a AY vector. And the A cosine theta business, what is that? That's the length of the AX vector. In other words, what we were really saying without realizing it is that there's a vector called AX, which has a length of A cosine theta and which points in the X direction. Like this is starting to look a little bit more obscure, right? But like, follow me. A page ago, I just said any vector that you ever have can be thought of as scalar vector multiplication. Any vector you ever have can be thought of as some unit vector in a certain direction scaled up by some amount or scaled down by some amount. Well, the AX vector is a vector of unit of length 1 pointing along the x-axis. We call that now from now on I hat times a certain distance. What distance? Well, not all of A, but A times cosine of theta, right? So I'm saying AX is a vector, which can be thought of as A cosine theta length times I hat. And similarly, I hat, AY vector can be thought of as A sine theta times J hat. And in the end of the day, then, okay, so again, in the end of the day, the vector A can be thought, well, it can be thought of as a simple product of length A times direction A. It can, and that's correct, and that's complete, but it's not going to do much for us if we're ever trying to relate vector A to any other vector B. So the other way to look at vector A, and this is what you were always doing in physics 203, you just didn't have the notation or the rigorous language for it that we sort of now need. The that vector A can now always be thought of as a sum of two vectors, A cosine theta I plus A sine theta J. And I'm going to move on in a second. Wait, okay, I'm just looking at the chat. Really, if nothing else, there's two takeaways here. One takeaway is anything we ever said in English in Physics 203 literally can be captured symbolically and can be used now in mathematical analysis directly. Like we can treat these vectors as objects and do math on them directly. And so whenever anything you ever believed or thought you or did understand about like a vector sort of involving two components, or by the way, or three components if you're in 3 dimensions, I'm now saying, yeah, literally that's true. Like a vector is literally the sum of products. It's a sum of vector components, component vectors, each of which is a scalar vector multiplication. Okay, so the vector A is literally the sum of A cosine theta I hat plus A sine theta J hat. That's all under the rubric of that's how important scalar vector multiplication is. It's just like how we actually construct vectors in our mind, even when we're constructing them from individual components. Okay, so that's number one. Then number two. So now, okay. Wait, is there anything else I have to? No. Okay. So then, hello. Just want to see how. Okay, yeah. So way number two. Way number two, vector by vector multiplication yielding a scalar. And we already know that, right? So way number one is scalar by vector, creating a vector. Hold on, I'm just switching the view on the screen. Okay. And then way number two is vector by vector producing a scalar. And you already know this is called the dot product. So because this is a way of measuring two vectors in a manner that produces a scalar, this is the way of looking this this is the way of trying to take direction out of the relationship or get a final answer that is not directional. So this one works by measuring the extent to which the two vectors agree on direction, right? So hence the cosine. We've already talked about that, but just notice again, even though I said made a big deal about it yesterday, notice that's a complete statement, the statement in white. Like you dot two vectors together and you get a number, which is the value of one times the magnitude of one times the magnitude of the other times the cosine of the angle between. You get a number, and that's your whole answer. That's it, the dot product. But then we said there's this third way of multiplying vectors. Vector.
It's my first and only appointment. It's from 2 to 3. And then I'm at the class.
Hold on, I'm trying to.
Bro, that shit. This guy.
Hold on,
No, I'm gonna go in person. Are you going in person?
Wait, David, you want to mute? Hold on, I'll mute him. I know it's a mistake. Okay. 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 So vector by vector producing a vector. So now I wanted to say more details about this. This is like where we left off yesterday, right? But now basically what I want to do now is say more about this cross because it's subtler and it's richer. I want to say more about this cross product by using this new unit vector notation. Okay, so where we left off yesterday, like let's say you're crossing two vectors, you're measuring not only how big they are, but how much they differ in direction, how much direction is playing a role in their relationship. So since the answer is going to involve more information, we take a step and say, let's give a name to the answer and then analyze, like, let's call the vector that is produced by crossing two vectors, let's call it C vector. Okay. Now, again, I notice I didn't do that with the dot product, but because I didn't have to and wouldn't have been right because the dot product didn't produce a vector. But now I'm looking at an operation that produces a vector. So let's pause and give that answer a name, call it C, right? Not like for all, like don't memorize that. But I'm just saying, like, there's a third vector now in our life. Once we cross two vectors, we're going to call it C. And what we said, if C is the cross of A and B, then what we said yesterday is C, the length of it equals AB sine theta, right? That's what we said yesterday. And again, it's for the same reason that the dot product is AB cos theta. It's the same reason, but in the other direction. Like sine of 0 is 0. Sine of 90 degrees, pi over 2 radians is 1. Sorry. So sine gets bigger as the angle gets bigger. Sine measures perpendicularity, not parallelism. So the magnitude of the cross product is bigger the more perpendicular two vectors are, right? But then we said yesterday, okay, but C is a vector. It also has direction. And we said, so now I can use this new notation and say, like, what's the deal with the direction of C? And what we said yesterday is that the direction of C is given by this thing called the right-hand rule. Whoa, hello. I don't know why that just happened. Sorry. Hold on. Ay, that's not what you need. Okay. Uh, okay. So the right-hand rule is just a convention. It's just like an agreement that we've all made. It could have been like if everybody did a left-hand rule, all of physics would still work. It's just that everybody has to do one thing or at least whatever, for physics to work. So we do the right-hand rule. I mean, someday, whatever. And I'm going to review the right-hand. The rule, it's like a little weird until you get used to it. But before I do it again, let me remind you that what's really happening with the right-hand rule, you'll know you really get the right-hand rule once you realize that this is all about crossing two vectors, A and B, right? Like remember, like we're assuming that there's vector A over here and there's vector B over here, and they're separated by an angle theta. And uh we're trying to find the direction of the cross product vector C. You'll know you really do get the right-hand rule once you realize that, like, by the time you're doing the right-hand rule to get that direction, you already basically know the direction. You're just trying to make a choice between the out version or the in version of that direction. Like what I'm saying is, if I look at the A and B and I have to do the cross product, what I know in advance is that the answer, vector C, will necessarily, definitely be perpendicular to both vector A and vector B. Like vector C is a measurement of the perpendicularity of A to B. So vector C will be perpendicular to A and B. And which is always possible, oddly, but the only way it's possible to find a vector that is perpendicular to two original vectors is that vector has to be perpendicular to the plane in which the two vectors were drawn originally. So vector C is necessarily going to be perpendicular to the plane of A and B, like my board, the computer screen. So vector C, even before I know the right-hand rule, I'm saying the vector C has to either pop out of the computer screen or pop into it. Sidebar, notice, but once we get to the cross product, once we're multiplying vectors in a vector way, we have to deal with 3 dimensions of space. I mean, quick sidebar. This is the first time this is happening to us in physics and possibly in math, like where we can't reduce our thoughts anymore to just like imagining just like 2 dimensions. Like we're now necessarily using all 3 dimensions of space to like think. So the cross product necessarily points in the one and only axis that is perpendicular to the plane of the original 2 vectors. So the only question is always, does it pop out of the plane or does it pop into the plane? And that's where the right-hand rule comes in. What we're basically saying is, well, it doesn't matter. I mean, it could be either one. And whichever one it isn't, we're going to like whichever one of those 2 options we'll call positive, and the other option is going to be negative. So really, we just all need a convention and an agreement on like which way to call positive. Like that's really right. So the right-hand rule is just a convention that allows us all to be on the same page as to which direction we're going to call positive and which negative. And so according to the right-hand rule, so here's where look, most of you are by yourself in front of a computer screen right now, so there's no embarrassment. I highly, I strongly request. In fact, my God, I should make this a portal. I should totally make this a portal. Like, I want you to join me in doing the right hand rule now. Like, nobody can see you, okay? But really, the right hand rule is like anything else in physics. It sounds like it makes sense, sort of, or it doesn't, but it doesn't mean anything until you practice it a couple of times. And when you practice it, you'll see that you have to practice it because you can get it wrong or it can be confusing, whatever, until you get it right. So here's the deal with so please join me. And if somehow I will make this a portal or remind me to make this a portal, like if somehow you could send me a thing that just says like, I practiced the right hand rule along with you when you did it, or God forbid you take a picture of yourself doing it and send it. That would be amazing. I really should make a portal for that. If you could somehow take a picture of not your, I don't want to be weird, but like of your hand or something, okay? Like do the right hand rule with me is what I'm saying. Here's the right hand rule. Like look at those vectors A and B up in the top corner of this sheet. The right hand rule says you take your right hand, even if you're a lefty, you take your right hand and you point your fingers. I'm going to wait, let me see if can I switch the screen? Hold on 1 second. Just hold on. I think there's a way. I know there's a way to flip the camera. Yeah, mirror my mirror. Okay. Whoa, that's awkward, but okay. Hello. Oh, sorry. Okay. So this should work if yeah, weird. Okay. So now I'm like lined up with the vectors in the thing, right? So, and it's the same, just because this is bigger, it's the same, right? Okay, same as that picture, right? So look at that picture, A and B. I take my right hand, I place my fingers along the direction of the first vector, vector A, like order matters. I take my fingers, I place them along the direction of A, and I play, and let's pause right there. Notice there's like a number. This is why you have to practice on your own. I'm saying place your fingers along the direction of A. Well, if you just listen to those words, it sounds clear. But if you try it, you'll notice there's a number of different ways that I could place my hand so that my fingers point along A, right? Like I could do my hand like any of these ways. But the key is that the next rule, the next instruction is curl my fingers toward the direction of B. Or put another way, some people like to say, have my palm face the direction of B. So what we're really saying in instruction 1 is like you could place your fingers along A in any way, but find the one and only one way that would allow you to comfortably curl your fingers toward B without like breaking your body, right? So place your fingers along A such that you could curl them towards B, and then you will find that your thumb points necessarily in one way, and that way is the positive direction of the answer of the cross product. Like in this case, if I curl from A to B, then my thumb points into the board, right? Now, you with me so far? First of all, and I'm going to write this down in a second, but notice into the board, we now have a name for that. Into the board, and this goes to what Aminata said, yes, or like you'll see it relates to like a correction that Aminata made Monday on positive and negative signs. If our coordinate system is this, like where X points out of the board, Y points to the right along the board, I'm saying board, like computer screen, and Z points up the computer screen, right? Then the answer we just got when we did the cross product of these two vectors A and B, when we go like this, our answer is pointing into the board. So what does that mean? It means it's going, our answer is negatively along the x-axis. Like x-axis points out of the board, we're going into the board. So that's the negative x direction. So what do we call that? Negative I hat. Like I'm saying right now, if you're following me, this is the new information. I mean, this is like what I didn't say Monday. I'm saying, oh, sorry, sorry. I'm saying, I'll do it on a new page. Like I'm saying, strictly speaking, this would be in this case, if A is going like that and B is going like that, then C is a vector whose magnitude is AB sine theta, whose magnitude is AB sine theta, but whose direction is popping into the board, which means its direction is the negative of I hat. Like, so put one other way, if I want to know the answer to the cross product, I could think of first a unit vector that points out of the board, like a vector that has length 1 and points out of the board. That's I hat, right? I hat would, I mean, it would be X hat, but in the world we call X, you get what I'm saying? Like a unit vector that points out along the X axis, which in the world we call I hat rather than calling it X hat. So you think of a vector called I hat, a one unit vector pointing out of the board. Then you scale that up by an amount, AB sine theta, and then you flip it, you invert it, you put a negative sign on it because actually we're going into the board, not out of the board. That's our answer. That is a vector. The vector negative, AB sine theta, I hat. Do you see what right? That's all the information is right there in that statement. And then notice, so stop me if you don't understand. Then notice, if you're following this, let's make up a new vector called D. Say D is B cross A, not A cross B, but B cross A, right? Same A and B. Like there's A, and there's B, and there's theta, right? Then vector D. So if in other words, I'm going to do the cross product now in the opposite direction, and you again should practice with me. You'll know you get the right hand rule if you see when you do it that order matters. Now, and I'm also going to say I'm going to do the right hand rule now to do B cross into A, same A and B, but I'm doing it in the opposite order, right? And notice again, if I'm understanding the right hand rule, I know even before I do it, my answer is either going to pop out of the board or into the board. My answer has to be perpendicular to the plane of A and B, but I don't know which, right? So I do the right hand rule. This time I place my fingers along B and I curl them up to A, and my thumb this time points out of the board, right? So D, and you should try that. And you should take a picture of your hand and you should send it to me. And that's weird, but true. Um, uh, uh, so then D this time would equal AB sine theta times I hat with no negative sign. So note what I'm saying is the cross product, unlike multiplication of numbers and unlike scalar dot products, the cross product is anti-commutative. Order matters. It makes the difference of a negative sign, i.e., in general, A cross B in general, by in general, I mean always, A cross B equals the negative, the negative of B cross A. And you'll know you're getting the right hand rule if you see how the right hand rule makes that necessarily true. Okay, we're almost. Okay, almost there. If you're following this, now I'm gonna warn you right now. I mean, we still have 19 minutes. Oh, thank you for warning me, which you totally didn't. With the 19 minutes remaining, I'll try to circle this back and like get answers, give you the rest of the answers of the homework. I will try to do that in a moment. which might involve a calculator. Yeah, but one last thing I have to say, I'm going to turn it to you now. I'm going to ask you to answer questions in the chat, like right now that you did not do for homework. So it's like spontaneous. Please put things in the chat, in the direct chat. Please put things in the direct chat so people, so you don't influence each other and it's not a race. I'm going to ask you some questions. Put answers in the direct chat, or put in the direct chat something like, I understand the question, but I have no idea, or like whatever, but just like be with me in the direct chat. Um, uh, so synthesizing all this material, I'm now gonna, like, this is spontaneous synthesis. In the direct chat, I want this answer. Oop, sorry. I'm gonna ask a couple of questions. Um, like given everything I just said, like I hat means the unit vector along the x-axis, and dot product, means like length of one times length of the other times the cosine of the angle between them. So I'm going to wait till I get at least three answers or threes. I have no idea, whatever. Till I have three responses in the direct chat. What is all? But there's an answer to this. Like always, necessarily, no matter what the situation is, I want to know what is I hat dotted with I hat. Like remember, I hat is a vector. Dot product is something you can do to vectors. So what is, so this is like a do now. Okay, I see one thing in the direct chat. Awesome. I totally answering my question in the direct chat. Do I want to say whether that person, and I will say that person is correct. That's awesome. But that close. I see something else in the direct chat that is the right idea, but I actually did. I see two things in the direct chat now. Okay, I see three. I just saw another correct answer in the direct chat, but I'm seeing a lot of answers that are thoughtful and definitely show that they're paying attention, but not all right, which means this is worth talking about. Interesting. I'm going to read great. I'm getting a lot of answers. Thank you. And I'll give you one hint. It is a number. Like there is an answer that's a number and it will always be that number. Um, okay, great. Oh, great. Oh, wait, and let me also wait. These are great. I see all the answers. I'm going to read them out in a second, and I will move on in a second. But that's awesome. Thank you for the participation. You should all submit for points. And those of you who are like weirdly, and if it turns out you got it wrong, you could submit extra for the wrong points, right? I mean, weird feature of this class, but one thing, this I that we're talking about is not, this is a bad coincidence. I know we spent a while on Monday talking about I, the imaginary, the square root of -1. That is totally a different I. That is not this. That is a bad coincidence. I know it's in the same week, but I hat literally means X vector over X. Like it means the unit vector from now on, the unit vector pointing along the X axis, and J is for the Y axis and K is for the Z axis. This has nothing. I just, because a couple answers, and this has nothing to do with imaginary numbers or square root of -1, even though it's coming up in the same week. It's just another math thing. So, in fact, I'm actually concerned enough about that if you happen to be a direct chat person who said something about the square root of -1, like I'm proud of you for paying attention, like, but please let me know that you are now clear that that is not this. But wait, okay, other than that, I'm going to look in the direct chat. I mean, so I'm just going to read out the answers. I heard one, I heard two, I heard zero in the chat. I heard one, I heard two, I heard one, I heard zero, I heard some a couple slightly abstract things. I heard zero, I heard one, I heard -1, I heard one, I heard -1, I heard one, I heard yes, sir. Okay, thank you for the yes, sir. Totally awesome. I heard one, I heard oops, one. Okay, so someone corrected the two from a one. Totally noted, totally noted. I heard one, I heard one. Okay, so I totally am getting participation. Thank you. So I'm going to cut to the chase and say, yes, I believe the answer is one. And I'll tell you what, and for all time, this is not just an example. This is like a thing to know about unit vectors. Like I had, like, I hat dot I hat, what it means by definition is the magnitude of I times the magnitude of I times the cosine of the angle between them. Well, the magnitude of I, again, it's not the imaginary number. I don't know what to tell you. Well, yeah, the magnitude of a unit vector, of any unit vector, always is 1. The magnitude of any unit vector is 1. And like someone said in the chat, if it's the same vector being dotted with itself, then the angle between it and itself is necessarily always 0, right? So the answer is 1 times 1 times 1 is 1. Now so I want to make it clear right away. That's the answer. So way to go, many of you, and way to go, and any of you who put like 0 or even 2, like clearly like are with me. I mean, just like so as long as you understand now, any unit vector dotted with itself, any unit vector dotted with itself, yields a numerical answer of 1. Oh. Okay. Oh, good question in the chat. Hold on. Let me just hold on. Good question in the chat. Someone's asking, can I explain? Oh, and it's not even direct chat. Good for you for asking that publicly. Can I explain why I equals 1? I'm a little unclear on that. Fair enough. First of all, again, let me say it's a bad coincidence. This is not the same I that we were talking about 2 days ago. It's not the imaginary number. Okay, this I really 100% means this. Like if you could picture what I mean by X hat, if you could picture like X hat means the unit, X hat is a vector that points along the X axis that shows you the direction of the positive X axis, but has a length of 1. Like any unit vector, by definition, a unit vector is a vector that points in a particular direction, but on purpose has a length of 1. So it's just like a unit. It's just a pointer is what a unit vector is. It's like a unit that's just sitting there showing you which direction you're going, but doesn't have any size so that it doesn't mess up other multiplications. Okay. So the unit vector for X, the unit vector for anything would have a length of 1. The unit vector for X would, you got it. Oh, cool. Okay. Awesome. Great. Okay. So that's why. Yes. So the length of any unit vector is 1 to everybody. I'm really glad the person asked that. So if we did this whole math right on the board, this whole thing that's in yellow, if I had done it to J's, it would have been the exact same logic and therefore the exact same answer. Okay. Awesome. But, and the person, Caitlin, I'm going to start making another portal for this too. Thank you, Caitlin, for the question. It was a perfect question. Thank you for circling back and saying you got it now, so I can move on, which I will. Like, remember, that's another portal too, like closing a conversational path or something it's called. But also, Caitlin, thank you. And I won't make a big, but thank you for going public with that too. Like, the more people can do that, the more gutsy people. Like, I'm impressed and grateful. Okay. So now get a little harder. We got 10 minutes. I want to do one more thing and then hopefully you can remind me to give you the answers to the other. But now a little bit harder. So again, I'm going to ask you to go in direct chat on this, all of you. Like the question now is, what is I hat crossed? Well, actually, I'm going to ask you 2 questions at once. First of all, what is I hat cross with I hat? I want that answer in the direct chat. But then the slightly harder question, what is I hat crossed with J hat? Now, I'm going to shut up. I want you to think about it for a minute. I want you to put 2 answers in the direct chat. I want you to put 2 answers in the direct chat. And I want you to think hard, especially about that second one. Please remember that the cross product of 2 vectors is a vector. So your answer somehow has to be a vector, or at least, in general, your answer has to be a vector. It somehow cannot just be a number. It somehow has to convey size and direction for it to be a proper answer to a cross product. So let's see what's going on. Ooh, I see things in the direct chat. All right, I'm seeing first of all, I'm mostly seeing two answers good, but let me remind you again, those two answers, or at least one of them, the two answers need to be vectors in some way. And some of them are that I'm seeing in the, all right, ooh. Awesome. Awesome. A lot of answers in the direct chat. But remember, there should be two answers in the direct chat. And yes, they should be vectors. But I'm seeing, dude, yes. Yes. All right. Very good. Okay. Very good. Yes. Okay. I'm not going to respond to each one privately because like we don't have, well, I'll read the, what I'm seeing in the thing is 0, 1, 1, J hat, K hat, 0, K hat, 1 in the J direction, which would be, which you could say J hat, K hat, K hat, K, 0, K, K, 0, K, question mark, K, unit vector K. That's a lot. We would say K hat. Okay, I think people are really getting it. I'm impressed. I'll say the answers. I cross I do believe is 0. Really specifically, I would say is like the 0 vector. Like it's 0. I mean, it's 0. It's nothing pointing in no direction. But and why? Why? Well, I think most of you got it. Most of you put good. I see. Okay, and when someone writes K, they mean cat. Fine, but let's not like let's say. I mean, I know it's hard to write a hat in the chat unless you're Dr. Seuss, but yeah, fine. But I cross I, just to be clear, I think all of you got this. I cross I would literally would mean I times sine of the angle between them, and then in some direction, but the angle between them is 0. So yes, any vector crossed with itself will produce no cross product at all because we're measuring perpendicularity, and no vector is at all perpendicular to itself. Right. So in other words, yeah, so I hat cross I hat is the same thing as J hat cross J hat, which is the same thing as K hat cross K hat. Absolutely. But I cross J now, okay, I and J are fully perpendicular, right? So I cross J would be I multiply would be I times J, like, and again, I'm not being careless, right? Like, if I just write I don't mean nothing, but I don't mean I hat. I mean the length of I hat, right? Like, that's why I have to sort of take the chat seriously. I hat cross J hat equals I times J, or I guess really, truthfully, I J, times the sine of the angle between them. Well, now that's not 0, that's 1. So I get 1 times 1 times 1. That's the length. Like I cross J produces a vector that has a length, but then, and I'm impressed that many of you realize, is a vector with a length of 1, but it's a vector, so it points in a certain direction. Well, what direction? Right hand rule. So you put your fingers of your right hand on positive I, curl them toward positive J, and your thumb points up. So absolutely, the answer, so okay, so to review again, I cross I equals the same thing as J cross J, which is the same thing as K cross K, which is 0. That is true. But now what you're telling me that I agree with is I cross J equals K hat equals 1. Like you said, like a vector of length 1 that points in the K direction, i.e. K hat. So from now on, I cross J equals K hat, like always. And similarly, J cross K equals I. If you just do the right hand rule, you'll see that. And K cross if you just do the right hand rule, you'll see that K cross I equals J. But now to be super clear, and you could just put it in any chat. What does J cross I equal? What is J hat cross? Just put it in the chat or just say it or whatever. What does J hat cross I hat equal? Negative K hat. Very good, person in direct chat. Right? And similarly, K cross J equals negative I, and J, what's the other? I cross K. Yeah. And I cross K equals negative J. And there's ways in other math classes if you can put these in a matrix or whatever and like memorize, but you don't have to, I mean, if once you understand the right hand rule, you could just see that this is all true. Okay. So that's important. It all seems very obscure and abstract, but it's like really important for math and physics, really. Now we have 3 minutes left. Let me see if I can quickly, I'll try to quickly hold on. See if I can. If I can, I can, I can't, I can't. Hold on. Where'd it go? Where'd it go? What? What? It won't let me. I have limited content. Well, that might be, apparently I can't even open. That doesn't make any, I apparently won't let me open math methods. All right, so if you want to remind me tomorrow, or I'll post them as a PDF or something, the answers to the rest of the dot products, cost products, but the bottom, well, I'll say this. This just circles back to what Aminata said Monday. Of the answers that I did give you, remember the answers I did give you, and then two of them I said like when there was two cross products in the sheet, and one yielded an answer whose length was 9, and one yielded an answer whose length seemed to be -9 or whatever. And so what I'm now saying is the proper way to say that. But I was like, but we don't know the direction. Is the direction in the page, out of the page, whatever? Now I would say, and I believe Aminata actually said this that day. The answer to one of them is 9I hat, and the other one is -9I hat. That's the actual answers to those two and you couldn't have known that before, but now you do. That's the way to capture the answer vectorially to a cross product. So those two answers. I don't know. Okay, so I'll leave it at that. -9 I hat and 9 I hat were the answers that we were discussing yesterday. So I'll see you tomorrow at 12:15. Have a nice day, and I'll hang out for a second for questions, but I do have a meeting coming in.
What, Professor?
Have a great, yes, thank you. Have a great day. I'm turning off the record.